Hi folks. The next thing we're going to learn about is percent yield. Percent yield is important in industry because it gives chemists a way to compare two different processes, maybe two different ways to make the same substance, and they can compare which method does a better job of producing the chemical that they're trying to manufacture. So let's do an analogy here, percent yield. Let's say I'm making my cookies. I've got this recipe and that should make 60 cookies, but what if I only made 58 cookies? What if I had some batter that stuck to the inside of the bowl and it just didn't make it into cookies and I could only make 58 cookies? I could calculate my percent yield. Let's have a quick refresher. How do you calculate percent? Percent is always the part divided by the whole times 100. Part divided by the whole times 100. So what percent of the possible cookies did I actually make? I only made 58, that's the part that I made, out of the whole that I expected to make, which is 60, times 100. And so you can calculate a percent yield using this formula. We're going to do the same thing with chemistry and our chemistry recipe instead of a cookie recipe. So, percent yield. The formula you need to know is actual yield divided by theoretical yield times 100. What do those words mean? Let me give you definitions for each of these kinds of yield. The actual yield is how much product you really make. That's always a smaller value than the theoretical yield. The theoretical yield is how much product you think you should be able to make from the ingredients you have. So in my cookie example, the actual yield was 58 and the theoretical yield was 60. The actual yield is always going to be smaller than the theoretical yield, and it's based off of what you really make versus what you think you should be able to make according to the recipe. Another way to think about it is that the actual yield is what you measure in the lab. Like you do the experiment and you collect your product and you actually weigh it to find out what you actually got from your experiment. The theoretical yield is theoretical. You calculate it. You calculate it on paper using the stoichiometry process that we've already learned. As I've already said, the percent yield is used to compare reaction conditions to determine what method works best for making your particular chemical. Okay, what's the procedure for calculating percent yield? The first step is to calculate the theoretical yield. You do this using stoichiometry. Remember, that involves writing a balanced equation, using the known amount of the limiting reactant, not the excess, the limiting reactant, to calculate the mass in grams of the correct product. And once you've calculated that mass in grams, then you know the theoretical yield. That mass in grams is the theoretical yield. The next step is to identify the actual yield. Usually this is given to you in the problem. They'll tell you how much product was actually made. The alternative is that this is an experiment you're doing and you're calculating, you're determining the actual yield by doing an experiment in the lab. Step 3 is plug those values into your equation to actually calculate the percent yield. So let's do an example. If you start with 45.8 grams of potassium carbonate and it reacts with excess hydrochloric acid according to this equation shown here, if you actually get 46.3 grams of potassium chloride, calculate the percent yield of potassium chloride. Okay. The percent yield questions get a little tricky because you're given, it looks at first like you've got two knowns for a stoichiometry problem. But this isn't just a stoichiometry problem. we're going to do percent composition or percent yield. So let's look at how to do this problem. Step 1, calculate the theoretical yield. I need to think about what's my known for a big stoichiometry problem and what's my unknown. So unknown, I'm wanting to calculate the percent yield of potassium chloride. So I don't know how much potassium chloride I'm expecting to get. That's what I'm trying to calculate. Okay, I'm trying to calculate how much potassium chloride I'm expecting to get. So my known value is 45.8 of the potassium carbonate, and I'm trying to calculate how much potassium chloride I'm expecting to get. So let's do this stoichiometry problem. I start with 45.8 grams, then I insert my conversion factors. Grams to moles of that same substance, potassium carbonate. Now I need to switch from potassium carbonate to a different substance, so I use my mole-mole ratio from the balanced equation. 1 mole of potassium carbonate for every 2 moles of potassium chloride. Those values cancel out. And my last step is to convert to grams of my unknown substance. The moles cancel out. 1 mole of potassium chloride has a mass of 74.55 using the masses on the periodic table. Doing the math, 45.8 times 1 times 2 times 74.55 divided by 138.21 and also divided by 1 and divided by 1 gives you a final answer of 49.4 grams of potassium chloride. Now, I say my final answer, but really this was just the first step in a percent yield calculation. I now know how much potassium chloride I'm expecting to get, 49.4 grams. I've done step 1 for percent yield. Step 2 is to identify what the actual yield was. This was given to me in the problem. I was told that the actual yield was 46.3 grams of potassium chloride. So now step 3 is to actually calculate the percent yield. The percent yield is the part divided by the whole times 100. So I'm going to do 46.3 divided by 49.4 times 100. And my answer will be 93.7%. So percent yield problems are long, and you need to keep track of what step you're on. The other confusing thing about percent yield problems comes in the very beginning, when you're just trying to figure out what's my known and what's my unknown. But if you read the problem carefully and you think about how you go about calculating percent yield, it's the actual mass of a substance divided by the calculated mass of the same substance. That is the information you need to calculate percent yield. Let's do another example. What is the percent yield of water if 138.0 grams of water is made from 16 grams of hydrogen and excess oxygen gas? Step 1 is to calculate the theoretical yield. To do that, I need a balanced chemical equation. Here's my balanced chemical equation for reacting hydrogen and oxygen to create water. Labeling my known. I know I'm starting with 16.0 grams of hydrogen, and I'm going to end with, I don't know how many grams of water. That is my unknown. So I need to calculate that for determining the percent yield of water. I convert from grams to moles of hydrogen gas using a grams to mole conversion factor, using the molar mass of a molecule of hydrogen. Those units cancel. The next conversion factor I need converts from moles of hydrogen to moles of water. I get rid of moles of hydrogen and I convert to moles of water, and I use my 2:2 mole ratio in the balanced equation. My units cancel out. My third conversion factor, I need to convert from moles of water to grams of water. 1 mole has a mass of 18.02 grams when I'm talking about water. My units cancel out, moles of water with moles of water. And I'm just left doing the math. 16 times 1 times 2 times 18.02 divided by 2.02 divided by 2 divided by 1. This gives me an answer to 3 sig figs of 143 grams of water. I've now calculated my theoretical yield, and so step 1 is done. Step 2 is to identify your actual yield. This usually comes from the problem or from whatever experiment you're doing, but in this case it comes from the problem, and my actual yield is this value. They told me what mass of water I actually made. Step 3 is to calculate the percent yield. I'm going to use the actual yield divided by the theoretical yield times 100. So I'm going to use my 138.0 on top, my 143 down below, and multiply times 100, and that gives me 96.5% yield of water. Let's do another example. When 5.03 grams of potassium chlorate is heated, it decomposes as shown. So I've already given you a balanced equation here. If 1.77 grams of oxygen is produced, what is the percent yield of oxygen? Okay. I'm telling you how much is produced, and I want to calculate the percent yield. I'm going to need to calculate how much oxygen is produced when I start with this much potassium chlorate. So I'm starting with 5.03 grams of potassium chlorate, that's my known, and I need to calculate how many grams of oxygen I have so that I can calculate the percent yield. Generally speaking, the substance that you're calculating the percent yield for is your unknown, unless it's a backwards question, which we're going to look at next. Calculating theoretical yield. I'm starting with 5.03 grams of potassium chlorate. I need to convert from grams to moles of potassium chlorate. The units cancel out. Now I'm going to need to convert from moles of potassium chlorate to moles of oxygen gas using the mole-mole ratio from the balanced equation. 2 moles of potassium chlorate for every 3 moles of oxygen gas. The units cancel out. And my last conversion factor is to convert from moles of oxygen to grams of oxygen. 1 mole has a mass of 32 grams. Units cancel out. So I do the math and I get 1.97 grams of oxygen gas. So my step 1 is done. I've calculated my theoretical yield of oxygen gas. Step 2 is to identify the actual yield. This is usually in the problem, and in this case, it's just this 1.77 grams of oxygen. Step 3 is to calculate the percent yield. I've got the actual yield divided by the theoretical yield times 100. So 1.77 divided by 1.97 times 100. And the final answer is 89.8% yield of oxygen. Here's a follow-on question from this same problem, from the same balanced equation. How much oxygen would be produced if the percent yield were 78.5%? This is kind of a backwards question. Here I'm telling you the percent yield, and you need to tell me how much oxygen would actually be produced. What is the actual yield? Now, this is a follow-on from the previous example. Normally, if you just got a question like this, you would have to still do your step one the same. You would still have to calculate the theoretical yield. But for this problem, we've already calculated theoretical yield. On the previous slide, we know the theoretical yield is 1.97 grams. We're not given the actual yield, but we do know the percent yield. Remember, this is the equation that we use to calculate percent yield. Percent yield is actual divided by theoretical times 100. So we're going to plug in our values. It's just that this time we know different values than we've known for any of the previous examples. 78.5 is our percent yield. We know that value. And we know our theoretical value, so we can plug in 1.97 in the denominator here. But it's the actual yield that we don't know. It's the actual yield that we need to calculate. So we need to rearrange the equation so that we can solve for this grams of oxygen in pink here. How do we do that? How do we get that all by itself? We need to undo all of the numbers attached to it. So if we're multiplying by 100, we have to divide away the 100. Whatever we do to one side, we have to do to the other. Because I'm dividing by 1.97, we need to multiply times 1.97. And if we do that to one side of the equation, we have to do it to the other side of the equation. So by multiplying by 1.97, I get rid of that value. By dividing by 100, I get rid of that value. And so what you get by rearranging the equation is 78.5 times the 1.97 divided by 100. Now that we've rearranged the equation, we do the math, and we get 1.55 grams of oxygen. So if we know ahead of time that our percent yield is 78.5%, then we expect to get 1.55 grams of oxygen in this example. I hope this helped.